Okay, this lesson is about periodic trends. What we will learn today is atomic size. How is it changing from left to right, that is, in a period and along a group from top to bottom. That means the atomic size trend in a periodic table. So the pattern in the periodic table, that is also called periodicity, depends on two main factors. The first factor is the distance between the nucleus and the valence shell. So when the number of energy level increases, the distance between the nucleus to the valence electron increases. And the second factor is effective nuclear charge, which we call Z. So let us go to each one and explain a little more details about it. The first factor, which is the number of energy levels, we can explain in terms of Coulombic attraction, which is nothing but the attraction between two oppositely charged particles. We have proton in the nucleus, which is positive, and the electron revolving around it, which is negative. So the attraction between these two charges, we can say that is directly proportional to the charge, the product of charges. So that means the force of attraction will increase when the charges increases. And we can say that when the number of shells increases, the distance between the oppositely charged particle, the distance increases. When the distance increases, the force of attraction will decrease. That means that is inversely proportional to the distance between them. So that's how we can explain the first factor while explaining the atomic size. So one of the reasons why the force of attraction decreases when the size increases, the number of shells are increasing, right? So when the number of shells are increasing, the valence electron will get shielded by the electrons inside the atom. So this is the nucleus. So we call this one as core electrons or inner electrons, and this is valence electrons or outer electrons. So the inner electrons will shield the outer electron from the attraction between the nucleus. So that is called shielding effect. So that shielding effect will reduce our nuclear charge, effective nuclear charge. So the second factor is effective nuclear charge. So we will consider this shielding effect as well to find that effective nuclear charge. So actual nuclear charge will not take part in this one. So actual nuclear charge is Z. So we will subtract the shielding effect by the inner electron. That will give us the effective nuclear charge. So let us explain the trend in atomic radius based on those two factors. So what is atomic radius? Atomic radius is nothing but the radius of the atom from the nucleus to the valence shell or the valence electron. But if it is bonded with another atom, the atomic radius is half the distance from center to center of those two atoms. So that means the distance divided by 2. So that is the atomic radius. But we are going to explain the same way for the atomic size and the atomic radius, the same explanation. So let us consider an atom from elements from second period. Okay, so for the second period, we will have two energy levels, two shells. So we can see an element with 3 protons and 3 electrons, 1 valence electron here. And when you go to the same period, to the next element in the same period, we can see 4 protons and 4 electrons. And the next element will have 5 protons and 5 electrons. So what happens here is the effective nuclear charge, you can see it is increasing. So that means the proton number is increasing. So what happens is the attraction between that nucleus and the outer electron increases because we have more proton there, right? So what happens? The size decreases. And now consider along a group. Along a group, what happens is the number of shells are increasing. When the number of shells are increasing, the distance between the nucleus to the outer electron decreases. So the Coulombic attraction decreases. So when the attraction decreases, the force of attraction decreases, what happens? The size increases. This graph explains the atomic trend for certain elements here along a period and along a group. So we can see this is the first group, hydrogen in the first group, lithium, sodium, and potassium. And you can see that hydrogen to helium, this is the first period, and then you can see the second period and third period. So we can see that the atomic radius increases from hydrogen to lithium and to sodium and to potassium. So the atomic radius increases because we can see only one shell here, and it is going up because a second shell is added here. So less attraction between the nucleus to the outer shell electron, and the third shell is added here, and fourth shell is added here. So the atomic radius is also increasing. But in the case of period, we can see that no shell is the same number of shells, but the number of electrons are getting added to the same shell. So the atomic size decreases because of that. Nuclear charge increases, so the attraction increases. So same explanation goes from beryllium to neon. So no new shell added. On the same shell, electrons are being added. So the nuclear charge increases, the effective nuclear charge increases, so the attraction increases, so the size decreases. Same goes here. This chart gives us the numerical value for the atomic radius. So we can see from top to bottom 37 to 265, and from left to right 265 to 145. So biggest atom will be at the bottom, and the smallest atom you can see at the top right corner. A small memory tip again is the snowman top to bottom increases, and the trend from left to right when the snowman falls, bigger to smaller size. So in the periodic table, we can see that francium is the biggest element, which is at the bottom first group, and you can see the atomic radius increasing from right to left and top to bottom. So an easy way to remember the size is the element closer to francium will be bigger than the element far from francium. So if the element is approaching closer to francium, we can remember it's going to be bigger. That's a shortcut to remember which element is going to be bigger when you compare two or three elements. So here is a question, which should be the larger atom and why? We had to compare sodium and chlorine. So for sodium, we know it is in the third period. So first step is to locate the period and group. So I will see sodium is in the third period and chlorine is also in the third period. And this is in the first group and this is in the 17th group. So I have, for chlorine, I have 17 protons, and sodium, I have 11 protons. And what I will think next is, so since it is in the same period, I have to think about the nuclear charge. So the nuclear charge is more for chlorine. So what happens? The attraction between the nucleus and the outer electron will be higher in this case. So the size is going to be smaller in this case. And they're asking us the larger atom. So sodium will be the larger atom. Next question, you can try yourself. Which should be the larger atom and why? Look in the periodic table and pause the video and find out your answer, then check your answer. Cesium should be larger atom because of the increase in orbital size in successive principal quantum level to accommodate more electrons. So lithium and cesium, it's along a group. So compare the size using the number of shells. So Coulombic attraction will be less.